Hello everyone, I'm Jiang from the Technical University of Munich. Today I'm going to present our work on privacy-preserving high-dimensional data collection with Federated Generative Autoencoder. This is joint work with Xuebing Zhou from Huawei Munich Research Center and Grossklags from the Technical University of Munich. In the era of big data, large and diverse quantities of user data, such as electronic health records and web browsing history, are frequently generated on local devices. This local data usually contain many attributes describing user profiles from different aspects. Collecting and analyzing the hidden correlations of this multidimensional data can help companies to obtain a deeper understanding of user groups and provide better services. However, the direct collection of raw user data may not only violate the increasingly strict privacy regulations, but also lead to serious privacy accidents. Local differential privacy has been considered a state-of-the-art technique for data collection. The definition of LDP states that a randomized mechanism M satisfies epsilon LDP if for any two inputs D and D', the probability of outputting any value Y is bounded by e to the power of epsilon. Here, epsilon refers to the privacy budget. The smaller epsilon, the harder one can distinguish the input pair from the output and the stronger privacy. In the data collection scenario, applying LDP perturbation on the local side ensures that the server cannot infer the real user data from the perturbed results, hence achieving strict privacy guarantees. Although LDP provides strong privacy protection for local data, existing algorithms are not applicable to collecting high-dimensional data. The increase of attributes will not only result in a higher computational complexity, but also a significant decrease in data utility. On the other hand, in recent years, many companies adopted deep generative models to learn the statistical properties of complex datasets and generate high-utility synthetic data for building AI services. However, these applications only focus on the scenarios where the real data are already stored on the server, yet do not consider the privacy issues in data collection. Therefore, solutions for collecting high-dimensional data with a good privacy utility balance are still greatly needed. With this motivation, we propose DP-Fed-WAE, a privacy-preserving framework for collecting high-dimensional categorical data. The main idea is to train a generative model in a private manner to learn the distributions of real local data and then generate high-utility synthetic data on the server side. The framework includes three key modules. First, we use the generative Wasserstein autoencoder for data synthesis. Moreover, we train the model using the federated learning mechanism, which only exchanges model parameters and always keeps the real data on the local side. Finally, we propose a novel randomization algorithm, SignDS, which provides strict LDP guarantees to the framework. Next, we will introduce each module in detail. In our framework, we use the Wasserstein autoencoder as the generative model. The WAE model contains an encoder Q, which compresses the original high-dimensional input X to a low-dimensional latent feature Z, and a decoder G, which maps Z to the reconstructed output X'. X' shares the same shape as X. The loss function is comprised of two parts: the reconstruction loss, which measures the distance between the input X and output X', and the latent penalty, which quantifies the difference between the latent space distribution QZ and a certain prior distribution PZ. Here, we set PZ to follow the standard Gaussian distribution. The goal of training is to find an optimal set of parameters that minimizes the reconstruction loss while restricting the latent space to follow the prior distribution. In order to prevent the server from accessing the real local data, we propose to train the autoencoder using federated learning. The training process goes as follows. In each global round, the server distributes the current global model to a group of local clients. Each client trains the model using his local data and computes the local update, which will be returned to the server for updating the global model. Although federated learning successfully avoids the collection of real data, recent studies point out that returning the local updates may still cause serious privacy leakage. Therefore, we propose a novel randomization algorithm, SignDS, to enhance privacy protection. The main idea is that instead of sending the complete local update, each client only returns the dimension index and update value of one important parameter. The server can then use this information to construct the sparse local updates and to update the global model. Since the parameter information is still related to the local data, our algorithm provides twofold privacy protection. First, we replace the real update value with a sign value S, which is randomly sampled by each client. The sign value is further used to determine a top K set that contains the dimension indices of the K most updated parameters. If the sign equals 1, we select the indices of the K largest values. Otherwise, we select the indices of the K smallest values. Next, we apply a private dimension selection algorithm, where the dimension index J can either be selected from the top K set with a probability of P, or be selected from the non-top K set with a probability of 1 minus P. We prove that the algorithm satisfies epsilon LDP guarantees. Finally, the random sign value and the private dimension index will be returned to the server. We refer the audience to check section 3.2 for more details. By summarizing the above design considerations, we present the overall workflow of our framework. First, the WAE model is trained between the server and clients under federated learning to learn the statistical distributions of real local data. Additionally, the SignDS algorithm is applied to prevent privacy leakage from the real local updates. On the server side, the dimension indices and sign values are used to update the global model. The training process is repeated for several global rounds until the WAE model achieves a satisfactory performance. After the model is trained, we use the decoder part for generating the synthetic data. Since the latent space distribution is restricted to follow the prior distribution, we can simply sample random latent features from the prior distribution and feed them into the decoder to produce the synthetic data. The generated data can then be used for downstream data mining and model training tasks. We evaluate our framework from both utility and privacy aspects using 4 open-source datasets. For the utility evaluation, we investigate whether the synthetic data preserves similar statistical properties as real data and can support AI training tasks. For the privacy evaluation, we use the membership inference attack to analyze whether the synthetic data can reveal privacy of real data. We compare the framework's performance with 2 baseline algorithms. Both algorithms directly apply LDP perturbation on the real local data, where the privacy budget is evenly allocated to all the attributes. We first use the average variation distance to compare the multivariate distributions of real and synthetic data. The figures show the results of 4-way AVD under different privacy levels. It can be seen that the AVD decreases with an increase of privacy budget epsilon, and our framework generally achieves a smaller AVD compared to the baselines. This indicates that the synthetic data generated by our framework can preserve better multivariate distributions in real data. Moreover, we find that for our framework, choosing different top K ratio alpha may slightly impact the data utility. According to the dimension selection probability, the alpha is inversely proportional to e to the power of epsilon. Therefore, the optimal choice of the top K ratio alpha is in general negatively correlated with the privacy budget. Next, we investigate whether the synthetic data have similar cross-attribute correlations to real data. To this end, we randomly pick 10 attributes for each dataset and visualize the correlation heat maps of both real and synthetic data. From the results, it can be seen that the correlation heat maps are very similar to each other, which again demonstrates that the synthetic data can preserve the statistical properties of real data quite well. Finally, we evaluate the data utility in AI training tasks. To this end, we train 2 classification models respectively with real and synthetic data, and test the models with a set of held-out real data. The figures show the test accuracy and the different privacy levels. It can be seen that our framework consistently shows a better test accuracy compared to the baselines. Particularly, when epsilon equals 8, the models trained with synthetic data only yield 1 to 3% of accuracy loss. The results show that the synthetic data can effectively capture the hidden patterns of real data and can be used for AI training tasks. In section 5.2, we also show that pre-training the WAE model can further improve the classification accuracy. Besides utility evaluation, we further perform the membership inference attack to verify the privacy of our framework. We follow the attack proposed by Stadler et al., where a privacy adversary aims to use a published synthetic dataset to infer whether a target record was used to train the generative model. To perform the attack, it is assumed that the adversary has a reference dataset, which shares the same distribution as real data. The adversary respectively trains a pair of generative models J-in and J-out using the reference dataset with and without a target record. Then, the synthetic datasets generated by both models will be labeled and used to train an attack model, which can be regarded as a binary classification task. Finally, given the published synthetic dataset, the adversary can use the attack model to infer the membership of the target record. Here, we report the attack accuracy of the 4 datasets and the different privacy levels. It can be seen that simply training the generative model without any protection may still cause privacy leakage, where the attack accuracy of all the datasets is more than 60% and even more than 70% for the census dataset. On the other hand, applying differential privacy can effectively reduce the attack accuracy. When epsilon equals 8, the attack accuracy is reduced by 8 to 15%. When epsilon equals 0.5, the attack accuracy is even close to random guesses. In conclusion, in this paper, we propose DP-Fed-WAE, an efficient and privacy-preserving framework for collecting high-dimensional categorical data. We further propose SignDS, a novel randomization algorithm to provide strict local differential privacy guarantees to the framework. Finally, we conduct extensive evaluation experiments and show that our framework can enjoy a satisfactory privacy-utility balance, and the generated synthetic data can replace real data for downstream data mining and AI training tasks. Thank you for listening.